Okay, we're going to talk about vectors in R2. And here are three examples of arrows representing vectors in R2. R2 is just you can think of it as the XY coordinate plane. So you can think of this blackboard as being part of the XY coordinate plane. Two-dimensional, flat space. Okay, now, a vector can go anywhere in the space. So this is the vector v. I can write the vector v down here as well. Now it can't change its direction, so hopefully I wrote this pretty parallel, I drew this pretty parallel to that. And it can't change its excuse me, can't change its length. So I think maybe I need just a little more length on there, but this is a representation of the vector v. As long as we keep the same direction, it's fine. And vector w, well, you know, I can do this. I could take the vector w and I could draw it this way. Okay, here's w. Okay, hopefully this has the same direction and the same length. So there's the vector v and the vector w, and they share this point. Now this is called the initial point. It's the initial point of v, the point opposite the head of the vector, and this is the initial point of w, the point opposite the head of the w vector. And the head of the vector, the very tip, is called the terminal point. So I'm not going to write those names down. It's pretty obvious what I mean. Initial point, terminal point, initial point, terminal point, initial point, terminal point. Now I drew these vectors with the same initial point. And there's a reason for that, and we'll come back to this in a minute. Or I could draw two vectors. Let's say u, which looks to be in about this direction with about this length, and v, like so. And we call this picture head to tail. Now, our definition of the sum of two vectors. Okay, well, the sum of u and v is just the vector that has the same initial point as the first vector and the terminal point of the second vector when the vectors are drawn head to tail. So u plus v is this vector. Now if I draw the vectors head to tail, I mean I just said they take the two vectors u and v, draw them head to tail. I could have drawn v first and then u second. So I could have had it like this. Here's v, and then here's u. So this vector is also v plus u. U plus v, or it's v plus u. And why is the terminal point the same? Well, if I've drawn these vectors correctly, the vector v has the same length whether I draw it here or here. The vector u has the same length whether I draw it here or here. So that these two sides are equal, and these two sides are equal. Not only that, but the vectors u and v have to have the same direction wherever they're drawn. So that v has to have the same direction here as it has here, which means these sides are parallel, and u has to have the same direction whichever way I draw it. So these two sides are parallel. So we have a parallelogram, and another way to look at it, of course, is we have similar triangles here. Now, you can make that argument, a geometric argument, shows that we have a parallelogram. So u plus v equals v plus u. Okay, so if we wanted v plus w, well, we happen to have drawn them with the same initial point. Had I drawn them with in the head to tail fashion, I could have just taken an arrow from the initial point of the first one to the terminal point of the second, and I'd have had v plus w. In this case, from what we've seen here and what we've said here, all I have to do now to get v plus w is just complete this parallelogram, because now I know that I'm going to have v here and I could have w here, so that my diagonal is v plus w. Okay, from the initial point of v to the terminal point of w. Put a head on w there. And of course that's the same as w plus v, because if I put them head to head in the opposite sense, they have to have the same terminal point. Okay, so here we have examples of three vectors and the idea of vector addition. Now there's more to vectors in R2, and we'll see a little bit more in the next clip.